Hello, and welcome to this new video about the angles and the arcs of a circle.
Circular arcs allow you to create a multitude of shapes with a compass, while angles organize polygons in time. A circle, as you know, is divided into 360 degrees. But why 360? Could it be related to the approximate number of days in a year? Partly, perhaps, but also because the Sumerians used a base 60 numeral system, and because 3 numeral system can be divided by many whole numbers, which I'll let you discover at the top of the image. Seen from Earth, the sun appears to make a complete revolution around us over the course of a day, and the shadow it casts from a stick or any other object allows a careful observer to tell the time. In 6 hours or 360 minutes, the shadow will rotate by approximately 90 degrees. In 60 minutes, it will rotate by approximately 15 degrees, which means about 1 degree every 4 minutes. The height of the sun at a given latitude can also provide an indication of the time of year depending on the time of day. And this brings us to something particularly interesting. Any ancient sacred building should normally contain this kind of information through the light entering the building or through the shadow cast by its highest elements, or another object, or even an opening in a pane of glass. We'll come back to this later, but even the Great Pyramid was used to indicate time. There were no clocks or calendars before the invention of the printing press in the 15th century. An angle represents a direction or an inclination relative to a base, a stake, or any other object placed at the top of a building and used to indicate time. This is called a gnomon.
A circle can be divided, particularly when constructing an inscribed polygon using a compass, which allows us to draw arcs and transfer distances. Circular arcs can also be used to construct certain spirals or ovals that approximate ellipses. One of the easiest polygons to construct is, of course, the hexagon, which we'll explore in Chapter 35. All you have to do is step the radius around the circumference to divide the circle into 6 equal parts. 60 degrees is therefore one of the most obvious angles to construct within a given circle. And if you connect every other vertex, you obtain an equilateral triangle containing 3 60-degree angles. It is commonly assumed, in my opinion, an idea that goes back to the Renaissance, that ancient builders always started with a given circle and divided it in order to construct a polygon. But I'm convinced that this leads us down the wrong path. You'll soon understand why. With this method, apart from the hexagon, you control neither the length of the sides nor their position, only certain vertices. For the triangle, we obtain the square root of 3. For the square root of 2. For the hexagon, 1, a very special case. And some of you will already recognize 0.618 for the decagon. In almost every other case, we end up with much more complicated values. I'll let you take a closer look at them.
On the other hand, starting from a single line segment, we can construct any regular polygon, with every side having exactly the same length as that original segment. It is all a matter of organization. We will come back to this step by step when we explore how to construct polygons. But how can we determine the angle of a polygon without actually measuring it? And what relationship does it have with the 360-degree circle? I'll let you explore these drawings. What do we notice? There is a continuity between the angles of the same polygon, since the polygon is regular. If we break down a polygon and extend its divisions to the right, there are always 2 additional divisions. 180 degrees, in other words, half a circle, divided by the number of sides of the polygon gives us the angle of the first vertex on the left, measured from the right-hand end of the polygon's base, where the small circles are shown. To determine the angle of the final vertex relative to the base, take the number of sides of the polygon, subtract 2, and multiply the result by the angle we just found.
For the triangle, 180 degrees divided by 3 equals 60 degrees. 3 minus 2 equals 1, and 1 times 60 degrees equals 60 degrees. For the square, 180 degrees divided by 4 equals 45 degrees. 4 minus 2 equals 2, and 2 times 45 degrees equals 90 degrees. For the pentagon, 180 degrees divided by 5 equals 36 degrees. 5 minus 2 equals 3, and 3 times 36 degrees equals 108 degrees. For the hexagon, 30 degrees and 120 degrees. For the heptagon, approximately 25.714 degrees and 128.57 degrees. For the octagon, 22.5 degrees and 135 degrees. We'll return to this in chapter 110.
If we mirror these polygons downward, we can see that there is always a correspondence between the directions of the sides and the intermediate vertices of the original polygons. If we then mirror the polygons again to the right, we discover other correspondences between the angles, resulting from the parallelism between certain diagonals and certain sides. And this creates some beautiful geometric forms, especially when these polygons have an even number of sides. We will come back to this in some of our analyses of architectural plans. In my view, the length of a circular arc is not particularly significant, since it is a curve and curved sections of buildings are relatively uncommon. What is more interesting is the circle itself, or sometimes the ellipse as a whole, particularly because of its relationship to the whole, as we saw in chapter 7 with the circle, and as we will see in the next chapter devoted to the ellipse.
Thank you for watching this video.
See you soon for more discoveries on our channel, Sacred Geometry.